Hi everyone, in this video we are going to practice assigning oxidation numbers. And so we're going to start off really easy with little ions and one diatomic molecule, and then by the fourth problem we're going to ramp it up to compounds that are not in the neutral state. So we're going to start off, like I said, with the easy problems. So here are 5 different pieces that I need you to identify the oxidation numbers in. Go! Alright, did you get an answer? Hopefully you did, but if you didn't, that's okay. We're still learning this, so don't get frustrated yet. So what we need to do when you're ever looking at an ion, if it gives you a charge and it's single by itself, it's one species, one atom, the charge of that atom is actually what the oxidation number is. So for example, when we're looking at chlorine minus, we automatically know that the oxidation number of chlorine minus, the chlorine anion, is -1. It tells us what the oxidation state is right there. Same thing for the potassium cation. The potassium cation is a +1 state, so our oxidation state is just +1. Now, oxygen gas is where it gets kind of tricky. The reason that I included the phase in here is because whenever we're looking at a diatomic molecule or any molecule that exists in its standard state as a certain way, its oxidation number is always 0. So, what do I mean by that? Well, if you look at the periodic table and you see that oxygen is red, you automatically know that oxygen in its standard state needs to be a gas. So that's what it says here, so we're good so far. The second thing is what we've learned from previous semesters or previous sections is that we know that oxygen always comes in twos. It's a diatomic molecule. So oxygen is never going to exist by itself as a single monatomic oxygen. It's going to exist as diatomic in the gaseous state. So when that happens and you're looking at something that is in its natural state, its oxidation number is always 0, okay? All right, let's move to hydrogen. Hydrogen has its charge. It's provided for us. It's a +1, so all you have to do is literally rewrite that number. And now we're coming to another quote-unquote tricky one. We're looking at lithium. Again, I included the state, so what you would do is look at the periodic table, automatically see that lithium is black, which means it naturally exists in its solid state as standard state as a solid, and so you automatically would say this oxidation number has to be 0 as well. Hopefully that makes sense. We're going to ramp it up a notch. Question 2. Here are 5 different molecules. I want you to assign the oxidation state on every single atom within the compound. Go. All right, did you get an answer? Hopefully you did. Let's start with water first. So the first thing I always do when I'm assigning oxidation states is I always try to assign oxygen first, followed by hydrogen, then anything else that's left over. So if we look at water, we're going to assign oxygen first. For this course, oxygen is always going to be -2. Always. So what we need to do is we need to take the oxidation state of hydrogen, and then we need to add it to the oxidation state of oxygen. And because we know that this overall molecule is 0, we need to make sure that this total charge gives us 0. So what I have here is my oxygen is a -2. We need this to be equal to 0. And then we have our hydrogen component, but there's 2 of them. So 2 times something, we'll call it x, plus -2 needs to be 0. The only answer that could possibly be to make this true is hydrogen has to have a +1 charge. So instead of putting x here, if we erase that, we could say 2 times a +1 gives us a +2 charge, plus a -2 gives us an overall of 0. So our charge is balanced, so we definitely have assigned the proper oxidation states for water. Let's do the same thing for carbon dioxide. So now for oxygen, we always assign it for -2. This time we have 2 oxygen atoms in this molecule. So -2 times 2 gives us an overall charge of -4. Now we see that carbon dioxide is overall neutral. So what we have to do is have 2 times -2 plus whatever our charge is for carbon needs to be 0. So we have -4 plus something needs to be 0. The only answer we could do here properly to make this math work needs to be that carbon has a +4 charge. Okay, so hopefully this is starting to make sense. So now let me do the same thing. I'm just going to erase this for the sake of space. Let's do the same thing for methane. So we have hydrogen here. We don't have any oxygen in methane, so we can't assign to oxygen. So now we need to move to hydrogen, So hydrogen we're going to just assume has a +1 oxidation state. There's 4 hydrogen atoms, so we multiply that by 4, giving us an overall of +4 for our hydrogen side. Now, we know that it's a neutral compound, so it needs to have an overall charge of 0. There's 4 hydrogen, so 4 times +1 gives us an overall charge of +4 for our hydrogen component. And so we know that the charge of whatever carbon is plus 4 needs to give us 0. The only number that can work to make this mathematically true is that carbon must be a -4, so that works out as well. All right, now let's look at carbon monoxide. Always, always, always start with your oxygen. If oxygen's -2, this is an overall neutral compound, or carbon, the only answer could be that carbon has to be +2. Just has to be in order for it to be neutral. All right, and now let's look at ethane. And so we do not have an oxygen, so we can't start with oxygen, but we do have a hydrogen, so we can assign this one first. So now hydrogen's going to be +1. There's 6 atoms, so +1 times 6 gives us an overall charge of 6. So we have our +6. Our compound is neutral, so it has to be 0. So +6 plus 2 times whatever the charge is for carbon needs to give us 0. The only thing that we could do is 2 times a -3 plus our +6 is going to give us a 0. So the only option here is that our carbon, for 2 of them, has to be an overall of -6. There's 2 of them, -6 divided by 2. The only way you could mathematically figure this out is if you solved carbon and gave it a -3 charge, okay? So carbon is -3, hydrogen is +1. Next question. For these 3, again, I want you to assign the oxidation numbers for every single atom within the compound. Go. All right, this is where it starts to get a little tricky. So now we just have to follow the exact same rules that we had before. Always start with oxygen, then go to hydrogen, then try to assign your other groups. After you've done oxygen and hydrogen, I usually look for my group 1 or group 7. So I'm looking for a halogen, so a chlorine, a bromine, a fluorine, because then I can give it a -1. Or I'm looking for an alkali metal, so a potassium, a sodium, and so on and so forth, because I can assign them a +1 charge. So let's start off with KMnO4 and see if we can kind of come up with our oxidation states here. So there's an oxygen, so we're going to start with that one. Oxygen's definitely going to have a -2 charge, but there's 4 oxygen atoms. So -2 times 4 gives us an overall of -8 for the oxygen atom. Now, manganese, that's a difficult one. That's definitely going to be something I do last, so I'm going to bump right over to my potassium and see if I can assign that. Now, like I was just saying, potassium is an alkali metal, so we know for sure it's going to do everything it possibly can to have a +1 oxidation state. So now what we can do is say our +1 from our potassium plus the charge from whatever manganese is minus the 8 or plus a -8, however you want to say that, from our oxygen. Again, this is an overall neutral compound, so it has to be equal to 0. So what we have to do is basically say 1 minus 8, which would be a -7. In order to make that 0, we have to make our manganese be +7. So 1 plus 7 gives us a +8. Subtract out our 8. 8 minus 8 gives us a 0. The only possible answer for our manganese oxidation state is definitely +7. Okay, really high, but manganese is notorious for having very, very, very high oxidation numbers. All right, so now let's move on to our next one, nickel oxide. So our oxygen component is going to have a -2 oxidation state. We know that. There's 2 oxygen atoms, so we multiply it by 2. This gives us an overall charge of -4. Now, we know this compound's neutral, so something plus -4 has to be equal to 0. The only way we can do this properly is saying 4. So 4 minus 4 definitely gives us 0. We've assigned these states properly. All right, let's look at this last one. This is the hardest one, in my opinion, out of everything in this video. So if you got it, kudos to you. I'm so proud of you. Oxygen, -2 charge. There's 4 atoms total, so -2 times 4 gives us a -8 overall charge. So this is a neutral compound. The only way for this to be properly done means that our iron, all 3 of them, have to have an overall charge of +8. So +8 minus 8 gives me 0. So that's how we balance out the charges. However, 8 divided by 3 is not a pretty number. So what we would say is that each iron has a charge of +8/3. It's a ludicrous value. It's a ridiculous value, but that is correct. If you are to properly assign oxidation numbers, you end up with iron with an 8/3 oxidation state. Weird, but it's true. So if you can do that problem, if you were able to do that, then you are in such good shape. All right, let's do one more. And this is where things really start to get tricky, because these are no longer neutral overall. So instead of setting this equal to 0, you have to set it equal to something else. I'll let you figure that out. Go. All right, did you get an answer? Hopefully you did, but if you didn't, do not get frustrated. This is definitely some of the most difficult part of assigning oxidation number, is when you're trying to do it for a compound that is not in the neutral state. So let's work through these together. So the first thing we have to do is identify the fact that each of these compounds have an overall charge. So for this one, it has to be equal, all of our charges have to be equal to +2. So what I'm saying here is the charge of uranium plus the charge of 2 of our oxygens must be equal to a positive 2, okay? So our overall charge of the compound's plus 2. That means our mathematically has to be equal to plus 2. Now, we already know that oxygen, we always assign that as a negative 2 value. There are 2 oxygen atoms, so we'll multiply that by 2, resulting with a negative 4 overall charge for our oxygen. So we can plug this in right here. So our 2 times our negative 2 overall is negative 4. So what we're saying here is uranium charge minus 4 must be equal to positive 2. The only way we can do this mathematically is if we assign uranium a charge of plus 6. 6 minus 4 gives us an overall charge of 2. A lot of people, for some reason, want to put plus 2 here, but that is not correct. Uranium is 100% plus 6 in this example. All right, let's move on to NO3 minus. So same thing as before. Nitrogen plus 3 of our oxygen charges, I'm already going to just pop in negative 2 right here because we know this already, must be equal to the overall charge of the compound, which is minus 1. So now, 3 times negative 2, that's a negative 6 overall. That must be equal to negative 1 when we add that to our charge of nitrogen. So I'll do it over here just so everybody's on the same page. Minus 2 times 3 gives us overall of negative 6. In order to have an overall charge of negative 1 for the entire compound, the only number that mathematically can be true for our nitrogen is a positive 5. So let's check. Positive 5 minus 6 definitely gives us an overall charge of negative 1. That works. You should always check this, okay? Always, always, always check your problems. Let's move on to AlO2 minus. Okay, this one was a little tricky as well. So just like before, charge of aluminum plus 2 oxygen atoms, which we know have an oxidation state of negative 2, must be equal to the overall charge of the compound, which is negative 1. I'll do it over here. Minus 2 times 2 definitely has an overall charge of negative 4. So we need to find some number. Minus 4 is going to give us an overall charge of minus 3. The only way to do this mathematically is to give us a charge of plus 3. So this works. 3 minus 4 definitely gives us a value of minus 1. Now, the one thing I want to point out here is that both nitrogen and aluminum end up with a charge of its group number. So aluminum is in group 3, nitrogen is in group 5. This is a very good way to check your math. It seems odd, it might seem like some random number that you have no idea where it came from, but just go back to that periodic table. If you get some bizarre number for nitrogen, you're like, ooh, plus 5, that doesn't seem right. If you're in that group number, there's a good chance that you actually have done this properly. It's not to say, that doesn't work forever, but it's just one way to kind of check and to kind of see, okay, I might be on the right track, but you can't necessarily prove that you're correct from that. All right, let's do the last one. So for this one, what we need to do is 2 times our value of chromium plus 7 times our oxidation number of oxygen, which we know is negative 2, and all of that has to add up to be equal to negative 2. All right, so 7 times negative 2 gives us a negative 14 charge, and then we have 2 times something minus 14 has to give us a value of negative 2. So let's do it over here. Negative 2 times 7 gives us an overall charge of negative 14. So something plus negative 14 has to give us negative 2. The only answer here has to be that our overall charge for chromium has to be plus 12. So 2 times something needs to be plus 12. The only way to do this mathematically is 12 divided by 2. There's 2 chromium atoms. The only answer possible is plus 6. So if we do this properly, we end up with chromium with an oxidation number of plus 6. Whew, that one was definitely tricky, but if you got it right, then you are on the right track. So practice, practice, practice. That's the best advice I can give you for this. Oxidation numbers is all about the number of times you've actually done this, you've drilled the problem. So put time into this. Good luck, take care of yourself, drink water.